Hello, my dear friend. Welcome back to Books and More, the space where we distill the core essence of profound works, helping you save time while keeping the soul of every page alive. Have you ever looked up at the night sky and felt a deep, quiet yearning to understand the secrets hidden within that vast velvet darkness? Today, we are embarking on a journey that transcends the boundaries of our daily lives. We are exploring A Brief History of Time, a masterpiece by the legendary Stephen Hawking. This book is a human testament to curiosity, written by a man whose mind roamed the furthest reaches of the cosmos even when his body could not. It is a guide that bridges the gap between the complex laws of physics and the wonder of the human heart. As we open these pages together, I invite you to wonder, where did we truly come from and where are we going? Does time always move forward, or could it one day flow backward? And in a universe that seems to have no boundaries, what is our place in the grand design? In the rush of the world, it is so easy to feel small and overwhelmed. But remember, you are made of the same stardust as the galaxies we are about to explore. Seeking to understand the universe is, in many ways, seeking to understand ourselves. I am here to walk beside you as we find perspective and peace in the great unknown. Wishing you a moment of stillness and profound wonder. Let us begin this journey through space and time together. Introduction to A Brief History of Time. I began this journey because I believe the fundamental questions about our universe belong to everyone, not just a handful of specialists. We spend our daily lives taking for granted the forces that make our existence possible, from the gravity that holds us to the Earth to the atoms that form our very bodies. Most adults eventually stop wondering why the universe is the way it is, but children never do. They ask why we remember the past but not the future, what a black hole really is, and how a universe that began in chaos could become so orderly. My intention was to lead an adventure through the history of the universe, from the initial point of a singularity with infinite energy to the vast cosmos we see today. The seeds of this book were sown after I delivered a series of lectures at Harvard in 1982. There were already many books about the early universe and black holes back then, but I felt none of them truly addressed the questions that drove me to study cosmology. Where did the universe come from? How and why did it begin? Will it ever come to an end? Modern science has become so specialized and mathematically complex that it often feels out of reach for those without a technical background. Yet I am convinced that the basic ideas concerning the origin and fate of the universe can be explained without complex mathematics. That was my primary goal. Someone once warned me that every equation I included would cut the book's sales in half. Taking that advice to heart, I decided to include only one, Einstein's famous formula, E equals mc squared. I hoped it would not frighten potential readers. Life has brought me many personal hardships. In 1985, I suffered from pneumonia and a subsequent operation that took away my voice. Before that, a neuromuscular disease had already confined me to a wheelchair. There were moments when I feared I might never finish this work. However, with the help of a computer system and a voice synthesizer, and the tireless support of my family and colleagues, I found a way to communicate even more effectively than I could before. Being a theoretical physicist is a stroke of luck in such circumstances because the work is done entirely within the mind. My physical condition has not been a barrier to exploring the furthest reaches of space and time. Through this work, I have tried to share the excitement of these discoveries and the ongoing search for a unified theory that might finally reveal the ultimate nature of the universe. our picture of the universe and the nature of space and time. A well-known scientist once gave a public lecture on astronomy. He described how the Earth orbits around the Sun and how the Sun, in turn, orbits around the center of a vast collection of stars called our galaxy. At the end of the lecture, a little old lady at the back of the room got up and told him that what he said was rubbish. She claimed the world is really a flat plate supported on the back of a giant tortoise. When the scientist asked what the tortoise was standing on, she replied that it was turtles all the way down. Most people today would find the picture of an infinite tower of turtles rather ridiculous, but we must ask ourselves why we think we know any better. What do we really know about the universe, and how do we know it? Our journey toward understanding began thousands of years ago. By the year 340 BC, the Greek philosopher Aristotle had already realized the Earth was a round sphere rather than a flat plate. He noticed that the shadow of the Earth on the moon during an eclipse was always round, and he saw that the North Star appeared lower in the sky when viewed from the south. He even noticed that when a ship comes in from the horizon, you see the sails before you see the hull. Despite these insights, he believed the Earth was stationary and that the sun, moon, and stars moved in perfect circles around us. This geocentric model was later refined by Ptolemy into a complete cosmological system. It was a beautiful, organized picture that the Christian Church adopted because it left plenty of room outside the celestial spheres for heaven and hell. It took nearly 2,000 years for a simpler and more accurate model to take hold. Nicholas Copernicus suggested that the sun was actually at the center, with the Earth and other planets moving in circles around it. This idea was dangerous at the time, and it was only after the work of Johannes Kepler and Galileo Galilei that the sun-centered model became undeniable. Galileo used the newly invented telescope to discover moons orbiting Jupiter, proving that not everything had to orbit the Earth. Meanwhile, Kepler realized that planets do not move in perfect circles, but in ellipses. This was a messy reality that was hard to accept until Isaac Newton published his work on gravity. Newton showed that every object in the universe is attracted to every other object. This single force explained why the planets moved as they did and why an apple falls to the ground. However, Newton's gravity created a new problem. If every star attracts every other star, why doesn't the whole universe just collapse into a single point? People back then preferred to believe the universe was static and eternal, perhaps because it provided a sense of comfort compared to the fleeting nature of human life. It wasn't until the early 20th century that Edwin Hubble made the landmark observation that distant galaxies are moving rapidly away from us. This meant the universe is expanding. If it is expanding today, it must have been smaller in the past. If we go back far enough, there must have been a time when everything was packed together in a single point of infinite density. This was the beginning of the universe, what we now call the Big Bang. To truly understand this expanding universe, we had to change our most basic ideas about space and time. For centuries, people followed the lead of Aristotle and Newton in believing that time was absolute. They thought that a second for someone on Earth was exactly the same as a second for someone on a distant star, regardless of how they were moving. Space was seen as a fixed, empty stage where events took place. But Einstein changed everything. He realized that the speed of light is a fundamental limit. It is the same for every observer, no matter how fast they are moving. This simple realization has profound consequences. If the speed of light is constant for everyone, then time and space cannot be absolute. Imagine two people, one standing on a platform and one moving on a high-speed train. If they both measure the time it takes for a pulse of light to travel, they will not agree on the time if they assume space is fixed. Einstein showed that time is actually relative. It depends on the motion of the person measuring it. This led to the idea of spacetime, a four-dimensional fabric that combines the three dimensions of space with the single dimension of time. In my work with Roger Penrose, we showed that Einstein's general relativity implies that the universe must have had a beginning in time. Einstein's theory also redefined gravity. Instead of a mysterious force acting across a distance, gravity is actually the result of mass warping the fabric of space-time. A heavy object like the sun creates a dip in this fabric, and the planets follow the curves of that dip like marbles rolling around a bowl. This warping even affects light, which we confirmed by watching stars appear to shift their positions as their light passed near the sun during an eclipse. We also found that gravity affects time itself. Clocks run slightly slower near a massive body like the Earth. This isn't just a theoretical curiosity, it is a reality we have to account for in modern technology like satellite navigation. If we didn't adjust for the way time slows down closer to the Earth, your GPS coordinates would be miles off within a single day. These discoveries moved us away from a static, clockwork universe into a dynamic one that is shaped by the matter and energy within it. We now know that space and time are not just a background for the universe, but active participants in its grand story. The expanding universe and the limits of determinism. For a long time, we lived with the comforting thought that the universe was a static, eternal place. But in the early 20th century, our view of the cosmos was fundamentally transformed. It began with the realization that our own galaxy, the Milky Way, is not the entire universe. When Edwin Hubble used the great telescopes of his time to observe distant patches of light, he discovered they were other galaxies, vast islands of stars separated by enormous reaches of empty space. To measure how far away these galaxies were, he looked at their brightness, assuming that if two stars were of the same type, the dimmer one must be farther away. But Hubble found something even more remarkable than the existence of other galaxies. By analyzing the light coming from them, he noticed a phenomenon known as redshift. Just as the pitch of a siren drops as an ambulance speeds away from you, the light from these galaxies was shifted toward the red end of the spectrum. This meant they were moving away from us. Most importantly, Hubble observed that the farther a galaxy was from us, the faster it was receding. This led to a conclusion that altered the course of science. The universe is expanding. The distance between galaxies is growing every second. This discovery was so radical that even Albert Einstein at first refused to accept it. He had introduced a fudge factor called the cosmological constant into his equations of general relativity just to keep the universe static. It was a missed opportunity, as his own theory could have predicted the expansion. If gravity is always attractive, as Isaac Newton had shown, a static universe should eventually collapse under its own weight. Only a universe that is expanding outward can stay balanced against the pull of gravity. Alexander Friedmann took this idea to its logical conclusion. He developed models that showed the universe could have started from a point of infinite density, where all the matter in the cosmos was packed together. We call this the Big Bang. In Friedmann's models, the fate of the universe depends on its density. If it is dense enough, gravity will eventually stop the expansion and cause everything to collapse back into a big crunch. If it is too low, the universe will expand forever. If it is exactly at a critical level, the expansion will slow down but never quite stop. For decades, scientists argued over whether the universe had a beginning, but the discovery of cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided the proof. This faint glow of energy reaching us from every direction in the sky is the fading heat of that initial massive explosion. The Big Bang marks a point called a singularity. It is a moment where the density of the universe and the curvature of space and time become infinite. At such a point, our current mathematical models and the very laws of physics break down. This means that even if there were events before the Big Bang, we could never use them to predict what happened afterward. From a scientific perspective, time itself began at the Big Bang. As we tried to understand these massive cosmic events, we were forced to look at the very small. In the 19th century, many scientists believed in the idea of determinism, famously championed by the Marquis de Laplace. He proposed that if we knew the position and velocity of every particle in the universe at one moment, we could use the laws of science to predict the entire future and past with absolute certainty. However, as we began to study the behavior of atoms and light, this dream of perfect predictability vanished. The first crack in classical physics appeared when we tried to understand how hot objects emit radiation. Standard theories predicted that they should emit an infinite amount of energy at high frequencies, which was clearly nonsense. Max Planck solved this by suggesting that energy does not flow in a continuous stream, but is emitted in discrete packets called quanta. This was the birth of quantum mechanics. This new science led Werner Heisenberg to formulate his uncertainty principle, which is perhaps the most significant limit on our knowledge. It states that you cannot measure both the position and the velocity of a particle with perfect precision at the same time. To see a particle, you must shine light on it, and the very act of hitting it with a photon, a packet of light, changes its velocity in an unpredictable way. The more accurately you measure where a particle is, the less you can know about where it is going. This is not a limitation of our technology. It is a fundamental law of nature. The uncertainty principle effectively ended Laplace's dream of a deterministic universe. We can no longer predict exact events. We can only calculate the probabilities of various outcomes. Even Albert Einstein was deeply disturbed by this, famously stating that God does not play dice. Yet, all our observations suggest that quantum mechanics is a correct description of reality. It explains why atoms don't collapse and why matter behaves the way it does at the smallest scales. We also discovered that particles can behave like waves, and waves can behave like particles, a concept known as wave-particle duality. In the famous double-slit experiment, individual electrons act like waves that can pass through two holes at once and interfere with each other. Richard Feynman expanded on this by suggesting that a particle does not follow a single path through space and time. Instead, it follows every possible path simultaneously. To find the probability of a particle arriving at a certain point, we have to add up all the effects of all those different histories. This brings us to a great challenge in modern physics. We have one set of laws, general relativity, to describe the gravity and expansion of the universe on a large scale. We have another set of laws, quantum mechanics, to describe the world of the very small. Both theories are incredibly successful in their own realms, yet they are inconsistent with each other. To truly understand how the universe began and where it is going, we need a theory that combines them both, a quantum theory of gravity. Until we find that unified description, the earliest moments of the Big Bang and the heart of the most dense objects in space remain a mystery. We have come a long way from the idea of a fixed and predictable world, and the journey toward a complete understanding of the cosmos continues. Elementary particles and the invisible giant. For centuries, we have wondered about the ultimate nature of the matter that makes up our world. Aristotle once believed that everything was composed of 4 basic elements, yet others argued that matter was made of tiny, indivisible pieces called atoms. It took nearly 2,000 years for us to finally prove the existence of these particles. We eventually discovered the electron, followed by the proton and the neutron, only to find that even these were not the end of the story. Through high-energy experiments, we found that protons and neutrons are themselves made of even smaller bits called quarks. These come in different flavors and colors, and they represent the building blocks of everything we see. In the quantum world, particles possess a property called spin, which tells us how they appear from different directions. Matter particles, like electrons and quarks, have a specific type of spin that forces them to follow the Pauli exclusion principle. This vital rule prevents two identical particles from occupying the same state, which is exactly why matter does not simply collapse into a dense uniform cloud. This principle is responsible for the stability of atoms and the existence of solid objects. Between these matter particles, forces are carried by a different class of particles that do not follow this exclusion rule. We recognize four fundamental forces: gravity, which is the weakest but acts over vast distances, electromagnetism, which holds atoms together, and the strong and weak nuclear forces that govern the interactions inside the atomic nucleus. Much of modern physics is dedicated to the dream of a grand unified theory that would show all these forces are merely different aspects of a single interaction. The story of these particles takes a dramatic turn when we look at the life and death of stars. A star is born when a massive cloud of gas, mostly hydrogen, begins to contract under its own gravity. As it shrinks, the atoms collide more frequently and heat up until they begin to fuse into helium. This nuclear reaction releases an immense amount of heat and pressure, which acts as an outward force that balances the inward pull of gravity. This balance allows a star to remain stable for millions or even billions of years. However, this fuel is finite. When a star exhausts its hydrogen, it begins to cool and contract once more. The fate of a dying star is determined by its mass. While I was a student, I studied the work of Subramanian Chandrasekhar, who discovered that there is a specific limit to how much mass a star can have and still remain stable once its fuel is gone. If a star is relatively small, the exclusion principle between its electrons or neutrons can provide enough outward pressure to halt the collapse, resulting in a white dwarf or a dense neutron star. But if a star is heavy enough to exceed this limit, no known force can stop the crush of gravity. As such a massive star collapses, the gravitational field at its surface becomes so intense that it warps the paths of light. Eventually, the star reaches a critical radius where the gravity is so strong that even light cannot escape its pull. This creates a region of space-time that is cut off from the rest of the universe, a boundary we call the event horizon. To an outside observer, any signal sent from the surface of the collapsing star would appear to slow down and become infinitely redshifted as the star approaches this limit. Once it crosses the horizon, the star continues to collapse into a point of infinite density, known as a singularity. This is the heart of a black hole, a place where our current laws of physics, including general relativity, cease to function. Even though black holes are invisible by definition, we have found ways to confirm their existence. We can observe their gravitational influence on nearby visible stars. In systems like Cygnus X1, we see a star orbiting an invisible companion that is far too massive to be a white dwarf or a neutron star. The only logical conclusion is that we are looking at a black hole. We also find evidence for much larger black holes in the centers of galaxies, where they consume vast amounts of gas and stars, powering the incredible brightness of quasars. These invisible giants are not just science fiction. They are a fundamental part of the history of our universe, representing the points where the very fabric of space and time comes to an end. Black hole radiation and the origin of the universe. I remember an evening in 1970, just after the birth of my daughter Lucy, when I began to think about black holes while preparing for bed. At that time, we did not have a precise way to define which points in space and time were inside or outside a black hole. As I moved slowly due to my disability, I had plenty of time to contemplate the path of light rays. I realized that the paths of light rays forming the boundary of a black hole, which we call the event horizon, could never approach one another. If they did, they would eventually collide and fall into the black hole itself. Because they must stay on the edge, the area of this boundary can only stay the same or increase over time. It can never get smaller. This discovery felt very familiar. It reminded me of a concept in physics called entropy, which measures the amount of disorder in a system. According to the laws of thermodynamics, disorder always tends to increase if things are left to themselves. A young research student named Jacob Bekenstein suggested that the area of the event horizon was actually a measure of the black hole's entropy. At first, I was annoyed by this idea because it led to a serious problem. If a black hole has entropy, it must also have a temperature, and if it has a temperature, it must emit radiation, just like a piece of hot iron glows in a fire. But by its very definition, a black hole is something that nothing, not even light, can escape. I worked to find a better mathematical treatment, expecting to prove Bekenstein wrong. To my great surprise, my calculations showed that black holes do indeed emit particles and radiation at a steady rate. This happens because empty space is not actually empty. It is filled with pairs of virtual particles that constantly appear and disappear. Near the edge of a black hole, one member of a pair might fall into the hole while the other escapes. The particle that falls in has negative energy, which reduces the mass of the black hole. To an outside observer, it looks as though the black hole has emitted a particle and lost a bit of weight. As the black hole loses mass, it gets hotter and radiates even faster, eventually disappearing in a spectacular explosion. This suggested that quantum mechanics might be able to remove the infinite points of density, or singularities, that traditional theories predicted. This same blend of quantum theory and gravity applies to the very beginning of the universe. In the traditional view of the Big Bang, the universe started as a point of infinite density where all the laws of science break down. After this initial explosion, the universe expanded and cooled. As it did, particles began to stick together. Roughly 100 seconds after the start, the temperature dropped enough for protons and neutrons to form the nuclei of elements like helium. Eventually, atoms formed, and gravity caused slightly denser regions of gas to stop expanding and collapse into galaxies and stars. However, this standard model leaves us with difficult questions. Why was the early universe so hot? Why is the universe so uniform on a large scale, with the background radiation reaching us at the same temperature from every direction? And why did the universe start expanding at exactly the critical rate needed to avoid collapsing back on itself immediately? One possible answer is a theory called inflation. It suggests that in its very early stages, the universe underwent a period of incredibly rapid, exponential expansion. This would have smoothed out any wrinkles and explained why the universe looks so consistent today. To truly understand how it all began, my colleague Jim Hartle and I proposed a new way of looking at the history of the universe. We used a mathematical concept called imaginary time, where the distinction between time and space disappears. In this view, space and time together could form a surface that is finite in size, but has no boundary or edge. You can imagine it like the surface of the Earth. If you travel across the globe, you will never find a cliff to fall off or a sign that says the end. The surface of the Earth is finite, but it has no boundary. If the universe follows this no boundary proposal, it means there was no singularity at the beginning of time. The laws of physics would hold everywhere, even at the very start. There would be no need to appeal to a creator or a set of new laws to define the initial state of the world. The universe would be entirely self-contained, neither created nor destroyed. It would simply be. This idea changes our understanding of our place in the cosmos. If there is no beginning and no end, but only a self-consistent set of laws, then the universe is a complete and beautiful system that requires no external intervention to exist. The arrows of time and the quest for a unified theory. I have spent a great deal of time thinking about why we perceive time as moving in a single direction, always flowing from the past into the future. It is a strange puzzle because the fundamental laws of science do not actually distinguish between the forward and backward directions of time. Yet in our daily lives, there is a very clear difference. I believe this distinction arises from 3 different arrows of time that all point the same way. The first is the thermodynamic arrow. which is the direction of time in which disorder or entropy increases. We see this whenever a cup falls off a table and shatters. We never see the pieces spontaneously gather themselves back together to form a whole cup on the table again. This is simply because there are vastly more disordered states than ordered ones. The second is the psychological arrow. This is our own internal sense of time, the reason we remember the past but have no memory of the future. I have found that this arrow is actually determined by the thermodynamic arrow. Whether it is a human brain or a computer memory, the process of recording information requires energy. This energy is eventually dissipated as heat, which increases the total disorder of the universe. Because we must increase disorder to create a memory, our subjective sense of time must follow the direction of increasing entropy. The third is the cosmological arrow, which is the direction in which the universe is expanding. I have argued that these arrows are linked by the conditions at the very beginning of the cosmos. If the universe started in a very smooth and ordered state, as suggested by my no-boundary proposal, then disorder was forced to increase as the universe expanded. This created the clear direction of time that allows intelligent life to exist and ask these questions.
This leads us to the ultimate challenge of my field, which is the search for a complete, unified theory of physics. For many years, we have been forced to use two different partial theories that do not fit together. General relativity describes the force of gravity and the large-scale structure of the universe, while quantum mechanics deals with the tiny world of atoms and subatomic particles. The problem is that these two theories are fundamentally inconsistent. I believe that a successfully unified theory must be built upon the uncertainty principle, even though Albert Einstein famously spent his later years rejecting that idea. He could not accept a universe governed by chance, yet the evidence suggests that uncertainty is a core part of how things work. Today, one of our most promising paths toward unification is string theory. In this view, the basic building blocks of nature are not point-like particles, but tiny, vibrating loops of string. These strings can vibrate in different ways to appear as different particles, much like the notes on a violin string. To make the math work, these theories often require space to have many more dimensions than the three we can see. We might not notice these extra dimensions because they could be curled up into a space so small that we cannot detect them, much like the surface of a straw looks like a line from a distance, but is actually a circle when viewed up close. As we look toward the future, I see three possibilities for our understanding of the universe. We might eventually find a final, complete theory that explains everything. Alternatively, we might find ourselves in an endless sequence of theories that provide more and more accurate descriptions without ever reaching an end. Or perhaps there is no theory at all, and the universe is just a series of random events. I am a cautious optimist, and I believe we are nearing the end of our search for the ultimate laws of nature. If we can truly find that unified theory, it would not just be a victory for scientists, but for all of humanity. It would allow everyone to understand the rules that govern our existence, and in that moment of discovery, we would truly know the mind of God.